He's Shaun Donnelly from the University of Sheffield, and he'll be giving us a walkthrough titled How to Talk to Your Documents. This should be interesting.
Yeah, I was hoping to just have a piece of paper here and just talk into it for 45 minutes, but I've got some slides for you instead. So, hi, Rinya, I'm Shaun. I'm a RSC at Sheffield, and looking forward to RSC happening there next year. So it's less train travel then. But I'm going to give you a walkthrough on how to talk to your documents. So it's an introduction to using natural language to query your documents with something called Retrieval Augmented Generation. Hands up if you're familiar with RAG. Okay, that's a decent split in the room. I'll take that. It's also co-authored by Edwin, down here waving in the front, and there is a GitHub repository with what I'm going to go through in. But I'm going to take you through it all mostly live anyway. But first of all, some slides to try and set the scene. I'm sure everybody has at least heard of large language models at some point recently. Jamie did a great job introducing them a minute ago, so I'll quickly run through this bit. But so they're the sort of large language models we're talking about here. They're built on the transformer architecture, and are trained on a ridiculously huge text corpora or image corpora if you're using vision models instead. But here we're focusing on text. So that's things from the internet, books, code, pretty much anything with words and they can get their hands on. And their job is to simply predict the next word, or in this case, token, because they're not one-to-one, in a sequence. So you'll have some words, the sky is, and then it will should predict blue, right? What are the strengths? So you talk to them, I guess. That's a fantastic strength compared to other ways of interacting with things. So you've got this natural language interaction. You can reason over context being some kind of information. So either you give it a huge document, maybe some historical texts to do with court cases, and they can reason over that and give you responses. So they can generate text, code, summaries for these things, and they are extremely flexible. They do have their drawbacks, however. So you have context length limitations. So just to elaborate, context length is effectively the window it sees. It's the amount of text that it is capable of ingesting or memorizing in any, if you will, in any one go. But it sort of has a finite amount you can use there. So massive documents, like maybe entire books, you couldn't just give a single model a single book. It wouldn't all fit in its context window. Hallucinations. So I'm sure we've all experienced hallucinations at some point, and I'm sure there will be plenty of hallucinations throughout this walkthrough. But it invents information. If you can't, they can, if they're not sure how to answer something from a context, then they will just invent your story, which I suppose is why lots of people use them for writing books. There are citation issues then as well, right? Like once an LLM has been trained on information, it's kind of like me asking anybody in the room to remember when they learned to speak. You can't tell me really when or where or how you learn certain words and phrases. And an LLM really can't either if it's just coming from the base model. It's trained on all this information. It can regurgitate facts to you to a certain degree of accuracy, but it probably can tell you how or why. So then they also suffer from up-to-date issues as well, right? They are training cards. I think GPT-5's training card was some point in 2024, so almost no information from this year would be available to it just from the base model itself. And then you have the security problem, which I think I've mentioned in every single talk. As particularly if knowledge of private data, or whether that's something you're hosting locally, it can't know anything about it. I have a database somewhere. It doesn't know this private data that I have. And if you pass it into a large sort of API-based language model like ChatGPT or Gemini or Claude, then you have security issues there as well. So you can sort of solve that with running local models like Olama. So here's a very sort of quick basic overview of RAG, right? You have something called a system prompt. I'm going to break all this down for you in a moment. But this is the general sort of vibe. A system prompt, a prompt, somewhere to store your documents, some documents you can bring out, a generator or language model, and then a response. So you ask it a question, it goes and gets documents, it's told how to handle those documents, and it gives you a response. And if we blow that out into a bit more detail, you get something that looks like this. So here's an example of RAG done practically literally. So the system has some instructions. So answer the user's questions using the provided context. If the answer is not in the context, then say, I do not know. So that gets fed in at the start. If you can imagine, the central section is your message chain. The blue bit is hidden to you as a user. So you type something in, it'll have these instructions, you won't see that. But you'll ask it, where did the Great Fire of London start? And it will then head into its document store, in this example, Wikipedia, pull out a document on the Great Fire of London, and then it'll extract it. So here we have the first paragraph extracted. So this is, again, something you don't see. So when you talk to it, it gets sandwiched, the LLM receives all three of these messages. You only see this one. However, any model does its retrieval, and then it gets passed to some language model, and it will give you a response. So based on the provided context, the Great Fire of London started on, realize that says where, not when, but it will consider that a hallucination, right? The Great Fire of London started on Sunday the 2nd of September, 1666, and then it was cited source. So that's sort of, we see this, right? You can see how all of that comes together. If I show you that in words, what that looks like in a much more exploded diagram is like this. So this is the process it goes through. Because even within the I take out my document, there are steps involved. So again, the user just sees this nice path from 1, 2, 3, and 4. But at some point, you have to be able to put your documents into a store. So you'll start out with a raw data sources, and extract the information however you want to do that. Like that could be anything from OCR, text extraction, you can crawl information off a web. You will then have to chunk it because we had that previously mentioned context length limitation. So chunking is literally just chunking. You just break it up into lots of smaller pieces, and then you embed those. You place that into a vector database, which I'll get onto in a second, and then you have a complete system here. You have a workflow that you can use for RAG. So before I get onto vector stores, I'm going to talk about embeddings. Who's familiar with embeddings? Yeah, probably the same people that said they're familiar with RAG. So embeddings take words and sentences and paragraphs, and they I always think it's transformed, but I always say translate, and I know it's wrong, but it translates it into this higher dimensional semantic space, right? It's represented as a vector, so just a string of numbers. And that kind of describes where the word, sentence, phrase, paragraph lies in this space. So it's analogous to like a two-dimensional map. You've got coordinates. We are, if it's just, maybe by Minecraft, if it's an X by Y, tell someone where they are on the surface, nice and easily. Maybe that's latitude and longitude. A three-dimensional map will have the same kind of thing if it's X, Y, Z, or if you're on a sphere, latitude, longitude, and how far away you are from the center. And that's nice and simple. Humans are capable of really visualizing that nice and easily. Embeddings go much further than that. They'll have 256 or 768 and many more embeddings or dimensions. And you can kind of imagine that trying to place it in the space. If I ask you all to describe an apple or if I give you some descriptions and I'll say all you can do is the color and how sweet it is, and the answer is an apple, and I say it's green and sweet, you could give me anything from like a pear or a grape. But then if I give you 256 different ways of describing your fruits, you can probably give me a very pinpoint description of exactly what fruit it is I'm talking about. So what I did was I took a load of vehicles and animals, fruits and places, and I embedded them. This one had 768, a vector of 768 dimensions. Did a bit of PC on it. I won't go into any detail with that, but I used the Nomic embed text model with Olama, and then I was able to represent them in 3 dimensions, right? So you can kind of see how the places are clustered together, the animals are clustered together, the fruits are clustered together, and the vehicles are kind of clustered together as well. So the whole point of this is, if they have a similar semantic meaning, they're going to be similar in this vector space, which is really important for RAG. So we can use those in vector databases then, which is how we store these. You can think of them as any standard database, like an SQL database, but you have some metadata, you have your content, and then you have an embedding, and your content is embedded. So a vector database stores the documents and their corresponding embeddings, and they're very, very highly optimized for this document search and retrieval. That's pretty much their entire purpose in life. They allow for the semantic retrieval of documents, and some sort of nice examples are Chroma, Pinecone, Postgres vector. There are many, 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 many different types of vector store, but they all have the same thing here. So you have if we're using it for RAG again, query, the query is embedded. So your sentence, what color is the sky, is embedded. It then looks for similar embeddings inside the data store, and then can match the document to it to pass that up to an LLM. So you put it in your context window and you get an answer. Some of the tools that we're going to be showing off today, and then this is not a LangChain tutorial, so I'm not going to get into the details of it too much, but I will preface that I had to change it the other day because they're deprecating all the previous version in like 2 weeks. So I had to very quickly update it to version 1 and be like, okay, this works now. So if anybody comes back to this in 2 weeks' time, they can still use it. But there are 3 principal components here. LangChain, you want to use that to get something working quickly. It's a Python library. It's got many, many integrations with many different LLMs, different vector databases. It passes the ecosystem in LangChain is huge, and they're very much plug and play components. And they support every major LLM and provider. And you use them for very simple RAG, very linear workflows, and kind of proof of concept projects. If someone wanted something, you'd slap it together in LangChain quickly. LangGraph gets more complex, so you have nodes and edges, ways of mapping different flows together, and they share a state. They can have robust interruption and resume functions. It's good for scalable workflows. So multi-step RAG, agents that need tools, some kind of memory or a human in the loop. And Langsmith, which is a platform which you use to sort of trace and follow what your LLM is doing. So good for comparing workflows, debugging hallucinations, and auditing things. And I will showcase that today as well. So the other tool that we're using today is Olama. Who's familiar with Olama? Has anyone used Olama? I think hands went up after as well afterwards. That's nice. So wrong way. This is Olama's website. You can jump on there. There's a huge number of models, and I would love to go through them with all of you, but I only have 45 minutes. So what we're going to do is, instead of that, I'm going to get onto the walkthrough. So there's a QR code again back to the GitHub repo, just in case you missed it. But again, this is all freely available. So we're going to start by turning this off and clearing it because it was never there. And then I'm going to just quickly start up a local Olama service. This is running on my machine using my GPU, and it's reasonably, let's hide that, reasonably simple to use. I start it up, Olama serve, and now I have my Olama service running. I'm leaving it in this one here, so it's it's a blocking process. So I'll leave it just in here in the background running, and then I want to look at, say, just show you the models that I have installed. Olama LS, which I think should be familiar syntax to just about everybody in the room. Oh, is it too small? Hope that helps. So I've got a plethora of models installed. I really wanted to show you pulling a model, but then I tested it last night on EduRoam and realized there was no time for that. Some of these models are quite large, even the smaller ones will be here for a couple of minutes. So I've got Gemma 3, 4 billion parameters, 12 billion parameters, the open weighted GPT model was recently released, 20 billion, and so on. And you can look into these models as well. So we'll say Gemma 3, and we'll look at the 4 billion parameter one. And lo and behold, it has about 4 billion parameters. It gives you your context length in tokens, the embedding length. So I will preface that this is the embedding length on a model like this is what it converts your sentences into or paragraphs into when you put it in. A quantization, which is effectively, you'll see people say quantize the 4-bit, 8-bit, 16-bit. It's just reducing the accuracy of the floats to make things just fit a little bit better in your GPUs. Series of compatibilities here, and then other sorts of parameters that you can modify with APIs. So you'll see some capabilities. Gemma, for instance, has completion and vision. Every LLM could really have completion if that's what it's for. But then if I showed you, say, GPT, OSS, 20 billion, then we have completion and tools and thinking. So it can't see things, but it can think about them. And then if you look at a embedding model, its capabilities are embedding. So it can't do completion. So if you try to run this and get it to answer you something, I don't actually know, I've never tried it, maybe I should, but it gives you information about this here, that it's just an embedding model. So now we'll move on to the walkthrough part. So we're going to use ChromaDB for our vector store in this. Everything's going to be saved locally on my drive. There is a series of, I've kind of jumped a few steps and pre-installed things. So there is all your pre-required packages here. This is here because I'm just jumping straight forward to LangChain 1, so that things don't break in 2 weeks' time. But everything you need is in there. And we're going to go through LangChain 1.0 for workflow orchestration and flexible provider integration, and a plethora of things, ChromaDB, OLAMA, document processing based on data from this conference. Similarity analyses, agent-based architectures towards the end if we have some time. And these are the sorts of things you'll learn, and I'll just go through them rather than talking about them. So we'll start off with any RAG flow. You kind of need to prepare your documents in some way. I feel like that's kind of key. So what we've done here is we've pre-downloaded the RSC con schedule. So if you go on to the website, you'll try and make this a bit bigger for anyone who can't see it. You'll find at the very top of the program, a little download button, downloads PDF. I pre-downloaded the PDF. And I use an integrated LangChain PDF loader, this PyPDF file loader, and pop the file in, and it will then load the documents. Now there are 11 documents in this. Well, there's 11 pages in here, but each one gets loaded as so-called document objects in LangChain. You can access that content by getting a document and then .page content. And the documents generally only do contain page content and metadata. That metadata will generally get loaded in and processed as you go through. The same with the page content, but you can kind of see here it's reduced it all down to some plain text with information about the schedule on page 1. You want to access the metadata, so we'll go the 8th page. So 7, it will give you just have the docs metadata. It tells you all this metadata, how it was produced, who created it, when it was created, a title, the last time it was modified, the actual source path of it, the number of pages, which page you were on, and then page label, which is then on 0 indexed for people to, kind of make sense of. So almost every LangChain loader, whether it's a web loader, a PDF loader, or a JSON parser, all of these things will load metadata in various ways, but the general structure should be the same. But you'll know what you're working with as you go through. The next step, wow, we're 20 minutes already. The next step is to chunk up your documents. Why do you want to chunk a document? Why can't I just give it an entire page. As I mentioned, it limits the size of page content in each document, and embeddings become more meaningful on smaller amounts of data. Like I say, describing a fruit in 768 dimensions is nice and specific, but embedding an entire book in 768 dimensions is probably not going to, you're not going to get a lot of information out of that. It's going to be very diffuse and sparse. But you can also group text together in a more logical way, like sentences, paragraphs. If you're using code splitters, you can go by, you're looking through Python code, just function headers, JSON splitting by different indentations, HTML splitting by tags, semantic splitting based on, it's more advanced, you pass it through an LLM to understand the document first and then see how it should be reasonably split up. We're going to be using the recursive character text splitter for this, and someone made this beautiful tool that allows you to kind of understand how it's split up. So we'll swap to the recursive text character splitter, and your chunk size in characters, you can sort of play with this and see how it will kind of try and logically filter things out, so no word gets cut in half when you're doing this. Chunk overlap doesn't generally, when you're trying to run the recursive character text splitter in Python, it requires one, but none of your chunks would overlap really. If you're using other types of character splitters, then you'll have this and you'll see how they overlap. So I would recommend having a play with this. It's a lot of fun. So pop back to our notebook. So we're going to use that recursive character text splitter, have the chunk overlap here so that it can look at either side of a chunk and make sure that it's splitting in the correct place. And I've got a chunk size of 200 characters. So I can run that by creating this text splitter and then split documents and give it the list of documents I've previously loaded in. And we go from 11 pages to 64 chunks. And if I was to reduce this down to 100, then I get 149 chunks. So this is one of those things that you kind of, as you're going through, you want to play with and try and figure out what works best for you. But we've massively increased the number of documents that we have. Once you've done your chunking, you need to move on to your embedding. So I previously mentioned that we're going to use Ollama for this, so I've still got that server running in the background. It's such an important part of the retrieval stage. Like, I cannot stress that how much it can change your outcome. Different embedding models are better for different things. We're just going to use the Nomic embed text one. It's a very popular embedding model that people use in Ollama, but there is so many on that. But like, it allows us to use our query to look for those similar semantic meanings in the text of our documents. So we need to have some embedding for it to compare to. So if you're using LangChain these days, you use this in embeddings helper function, and it's fantastic because it helps you wrap up all of what used to be rather complicated and frustrating code into one line. However, because of the sort of modular nature of LangChain, you may require additional packages. So we're using Ollama, so I also have LangChain Ollama installed, but I popped them all here so that anybody who wants to go back through this can see what packages they should be using depending on who their providers are. And then the nice little caveat of referring to provide a specific documentation when using them. They have different arguments. But for the most part, they all work like this. I import my embeddings function. I then create a Ollama embeddings object. I give it information about what model I want to use, what provider I want to use, and then you can just embed your documents. Now, when you're embedding something with these, they require, it's rather misleading. You say embed documents, but what you're really embedding is the text from the documents, hence every chunk. I've got the page content out, I put it in as a list of they're just strings, and then we'll run that, and we had 64 pages before documents, and now we have chunks, now we have 64 embeddings, and the length of a single embedding, just to confirm it, is 768. So that matches up with the model that we were looking at before. So with it capturing, it's, again, the embedding models, they capture the meaning of words that can be compared without having to use keywords. So if you're trying to search a database and you have a typo, just say using an SQL database, you have a typo in some way, you're not going to find the information you're after, and that can be really frustrating, especially if you're interacting with natural language. And it keeps on making, rather than, I don't know, say colors, it keeps on searching for color. That's not, that wouldn't work. So you'll transform them into these embeddings instead. Embedding literally just for clarity's sake is a list of numbers. Space generally between 0 and 1, I believe. I don't think I've ever seen them go any further, but they're so specific to your semantics. So once you've got your embeddings, you're going to need a vector store. Obviously, you could set up the vector store first, but I'm just setting up in this order. I'm storing it in a folder or with a persistent directory, so that it's local. So if I needed to copy this between one machine and another, I could. There are many different ways to do vector stores, as I mentioned before. You can even just store them in memory if you really want to. But to do that, you create a chroma object from LangChain. You need a collection name. So you could have one chroma database with many different collections in. So those collections would be analogous to databases in SQL. You have to give it this embedding function that I've created previously, because it needs to know how to retrieve the embeddings and what they should look like. So for everything that you put into it as something to compare to, it needs to make sure that it's got an embedding model to go through as you go through. So the previous step was manual embedding. This is automatic. So with this embedding, you can I create it here. I also just empty it just to make sure that it's fresh every time I go in, because otherwise you end up with the same document 100 times. But it creates the vector store, and then we add our documents like before. And this time you can just add them as document objects. To the benefits of just using the vector stores directly, you no longer have to extract the page text. But if for any reason you wanted to use an embedding model like I did before, that's absolutely fine. So we add the documents as they go in. The documents are embedded as they're added to the vector store. So they create the embedding that you see behind the document in the slides. And just to sort of prove that, we will retrieve a document. So vector store.get, this is a manual one. This adding documents returns a list of IDs, so I can use the first ID. And by default, this method doesn't include the embeddings to show you. So they are there. If you ever do just document.get, don't include this bit. It doesn't show you the embeddings, but they are definitely there. But it looks something like this. A unique ID, these embeddings in there in some lengthy array, but then the metadata as well. So as the source, the page label, the creation date, how many pages the entire document has in total, like we saw previously. So retrieval, wow, really getting off time already. Retrieval, I'll start moving through this. This was more a bit of something I found more fun about retrieval. It is like when you're using it to retrieve information with these embeddings, we use something called a cosine similarity. I'm not getting into that. There are many different types of ways to compare vectors, but I've just gone ahead and created some manual ones here. So you can see how I've gone through embed query, which is just one nice line of text. I can calculate my cosine similarity, and then I do this to show you how the similarities come back. So these are the things that I embedded. What is machine learning? What are neural networks? What is deep learning? The Eiffel Tower is in Paris. What's the capital of France? And then I am not pronouncing the French. I don't know if Roman's still in the room, but if you wanted to try that, you could. But the whole purpose of that is to go, well, neural networks and deep learning are kind of in the same thing, in the same domain. So they have an all right similarity. Machine learning and deep learning, again, semantically similar. So you get a score. Best score is 1, by the way. Worst is 0. And again, deep learning and neural networks, they kind of have a similar semantic similarity. However, when you get to trying to compare what's the capital of France and the Eiffel Towers in Paris, it's very clear that they are not related at all. So these embeddings are very good at separating out that semantic context. But then, something I found really exciting, and I had to show it off because I was really excited about it when I was playing with it. Embedding models are capable to train directly of crossing language barriers. So here, what is the capital of France, and then the French equivalent, have a very similar, have a high cosine similarity, so semantically similar, despite the fact that the actual text is completely different. So if you choose a good model, then you can probably use something that can interact in multiple languages without you having to translate a database. So we'll try some retrieval by similarity search. So I'll go, what time is the walkthrough on retrieval augmented generation? So this session, and I get 3 documents back. This K here is the number of documents it should return. By default, it's 3. You can modify that as you wish. And I print the first document out, and it should be a chunk, and it starts talking about deploying with Kubernetes. Okay. Oh no, there we are. Retrieval augmented generation is in the end here. So it's pulled back the document that's got the right kind of information in. We can then format that. So it would look, all the documents now look like something like this, where they're a bit easier to read, and subsequently easier for an LLM to pass. Depending on how big your information is, you don't want to be filling it with just tons of tags for things at this stage. So this is just the text, and we can see how it's cut over it's retrieved 3 documents, and this is what it's decided to do in them. But it contains the first information about this session, which I think is obviously what you want. So then you'll do the LLM integration. This is again just another slide, another section with your chat model, how you initialize a chat model, one line again, the same components and modules. And if I run this, I'm going to ask Gemma 3, 12 billion, what talks are on at 3 p.m. at Tuesday. I realize I'm going quite quickly now. But what talks are on at 3 p.m. on Tuesday are RSCon 25. Now, it shouldn't know anything about RSCon 25, really. I mean, it's not been trained on that kind of information. So I'm running this in the minute in the background, and then we'll see what it comes back with. So at 3 p.m. on Tuesday, if anybody was at any sessions at 3 p.m. on Tuesday, then it's The Importance of Documentation for Researchers by Emily O'Boyle, Reproducibility in the Age of Generative AI by David Schneider, and Balancing Speed and Quality in Research. So this is just a straight up question. There's no context to this. It's just gone and hallucinated an entire session, like list of sessions for Tuesday at 3 p.m. And we can view the whole schedule here at rscon.org/schedule. So it's now inventing websites as well. So what we'll do is we'll set up a template. This template is used to just give it information. So currently the previous step, raw model. No context at all. It just makes stuff up. So we're going to give it some structured information. So helpful assistant that provides information about RSCon 25. The context will go in here, and then a human question in here. And you can format these when you come to using them like this. So we'll go ahead and do this. We'll give it now the LLM, so it's called invoking. Excellent. I didn't run that cell, that's why. So we'll do some RAG on it now, and I'm going to manually do this. I'm going to give it some context. So the query I'm going to ask is, what is RSCon 25? And I'm going to say that it's a conference for research software engineers hosted here. And now it'll do some processing. I will see what that response is. And lo and behold, it has gone and given me exactly what I wanted. In fact, it's almost the same string back, right? So it would look like I've copied and pasted this. But it has tried to cite it as well, which was an important instruction up here. So we'll do a sort of pipeline here. This is entirely new. I threw this together the other day because of the changes. So a standard RAG pipeline is nice and straightforward. You go, it's a quote unquote chain. You start at the beginning, you move through, and this is what it looks like. The state is just what holds the information. And if I run this now, again with the same system prompt, a place for it to put its context. The context is retrieved here with the vector store similarity search. I'm only returning 1 document. Maybe let's make that. Okay, sorry. Let's make that 3 documents. So it will retrieve that by my query, which it's retrieving from the preview from the state. And I'll run this. You create because they're moving to everything to agent now. So you create this agent, which is just the instance that you'll use. I generate a response, I print the response, and Deborah Uda's Retrieval Augmented Generation is a talk/presentation from 12:30, 1 in the Oculus Atrium, and that's on page 9. Now, that's immensely frustrating because that's not what it did earlier on. But that's what I mean by how important your chunking is. So I could look at what that context looked like and just copy and paste this into a new cell. Now that's going to need to do more things. Let's bring the whole thing down here, and then I can put the query in. And the question was what time is the session? What room is it in? And indent that so it doesn't get angry with me. And then we can look at the context. So this is what the context ended up looking like. It's put the source information in, but the first one it's retrieved is this, and it kind of decided, in fact, it's decided that the session is down here. So having those additional documents was probably bad. If I reduce this down, so obviously relying about the correct context and try again, let it generate. It's now 1:30 till 3 o'clock, which I think is the time of the previous session that was in a different place supporting DRS operators. Now, this is a data quality problem. This is why it's so important that chunking is something you want to play with, you want to experiment with, but it's kind of proof of concept that you can retrieve information that's not hallucinated. Okay, it might have put the things together in the wrong order, but everything in there is factual in some form. And that worked so much better earlier on. But I promise you, RAG does help reduce hallucination. So we'll do that here. We'll give this a go. My question is, what's being served for lunch at RSCCon 25? And I'm going to just pass that straight through to the model. And this is just a straightforward lang chain. It does the same thing every single time. You go in, it tries to retrieve documents, it pumps that into context, and then it gives you something as a response. So this first one has no response, no RAG response. So Saturday, November the 2nd, we all had global flavors for lunch as a theme, and we got our own Mediterranean bowls. So that's exciting. On Sunday, November 3rd, we got comfort food in a series of different comfort foods. I really have to start wrapping up in a second. However, the right thing happened with the RAG response. It doesn't know. It doesn't know what we had for lunch. And every time I run this, we'll get a different hallucinated lunch schedule, but it will return I don't know every time. If I then change this query to, is there a session on JAX at RSCCon 25? Let's try that. So the reason it gives the wrong speaker is because the PDF, when you pull it off the internet, doesn't have the actual key call names in it at all. It shows the session chair. So according to Deborah, will be the speaker for all of the sessions today here. So the no RAG response thinks that there is a JAX session here. So this is mildly embarrassing. But the JAX session at RSCCon 25, maybe we'll do one that I know works like this session. Is there a walkthrough? There we go. A walkthrough on Retrieval Augmented Generation. I imagine the LLM is going to be eager to please again. It's going to tell me, yes, there is. And then the RAG should come back with something, hopefully telling us what it told us before. Should use a smaller model. So while that regenerates, we'll talk about the citing. Oh, there we go. That was the one that I had before about JAX. So this took forever to generate something about a deep dive on, so AI DevCon now, it's not even RSCCon 25 anymore. It's an intermediate thing. It's a ticketed event. You all had your passes to come in here. But this is one specific RAG walkthrough. But the RAG response is, yes, there is. There's a RAG session presented by Deborah Udo, taking place from 1:30 to 4:30 in this room at the very least. And the page label is correct. It was on page 10. So you can have some kind of source with it. I'm gonna speed up a little because this was supposed to be 45 minutes. But it would be the same here again. If you can cite your sources, I've shown it here. RAG can address the issue of citation by having the right page label. I would like to show you Langsmith, but I'm not going to now. It's a tool that you use for monitoring the behavior of workflows. It's the links there. It's free to sign up to. It's super easy to set up. It's a single environment file. You pop it into something like this. I realize I'm going to have to delete that API key now because it's recorded. But you pop that in there, and then it's a quick and easy setup to do that. The examples that you go through that we've been through in the walkthrough were just very straightforward ones. There are also agents that you can use, which are all more automated with this kind of flow. You pop in a query in, you get some external knowledge. It can call functions intelligently and pass it through to an LLM, and that's time. There is an example of it here that I can have people go through when you pull it up on your own machine. But yes, if there are any questions.
Thank you, Shaun. You mentioned that there are many models for embedding. Do you know if there are any performance advantages or other trade-offs between these models?
Yes. So smaller models are not as good as bigger models, which I think is kind of it almost sounds like it goes without saying. However, you'll find that that's not always true depending on what's going on. Sometimes a smaller model can capture smaller pieces of information better than a larger embedding. You can kind of be over specific with if you know using like one of OpenAI's ones, 3072 vector dimensions for a single word is overkill, because that requires a significant, if you're running something like locally, it would require a lot of resources, whereas if you use a smaller model, you could get away with getting the same kind of accuracy, but with a significantly better performance threshold. So it kind of depends upon what you're using. Some models will be better trained on specific domains. Other models will be more general. So it's kind of reading what the person who produced the models says about their model, and then giving it a bit of trial and error yourself as well to see if it's doing and performing how you'd like it to. It's all semantics. So you should kind of be obvious to you whether or not it's working or not if it's coming back with the correct context.
Thank you. One more question. What are the minimal hardware requirements to run a functional RAG-enabled LLM?
I suppose that depends on the model you're running. So this Mac can run rather large models. Like say there's a 20 billion parameter model that I know I can run on here. That would be capable of reasoning over very large pieces of context. You need less chunking. But for the most part, I mean, if you've got an all-right GPU that can load the Olama models in locally, then there's no reason. There's not that's pretty much it. Just the GPU. You need bigger, if you want to have bigger models, you need a bigger GPU, but otherwise, a reason I think I feel an RTX 3060 in my workstation that can host Olama's 3.28 billion model quite comfortably and works quite well.
Right. That's all. Thank you, Shaun.